Well, welcome back, dear listener, to Standing on the Shoulder of Giants. And this week we'll be looking at the discoverers of exploding stars. At around 2 a.m. on February the 24th, 1987, a Chilean engineer named Oscar Dunhold stepped outside with his coffee during a break from his job. It's an experience that night shift workers all over the world have probably shared. Holding a chipped mug of coffee, idly stirring in milk or cream or sugar, and taking a break from a long evening's work to look up at the sparkling stars of the sky. But Oscar was a decidedly unusual night shift worker, and what he saw in the sky on that night would mark a unique moment in living human history. Oscar was a telescope operator at Las Campanas Observatory in Chile. Telescope operators have crucially important jobs in astronomy. They typically work at a specific observatory and are trained scientists and engineers who specialize in the immensely complex operations of the world's best and largest telescopes. Astronomers today don't typically move and point telescopes themselves. We may know about the physics happening deep inside stars or during the earliest moments of the universe. But the motors and the gears and the workings of world-class telescopes are best left to the professionals, specially trained operators like Oscar. Oscar was a seasoned telescope operator and had spent nearly 2 decades learning the ins and outs of telescopes, working with astronomers who visited the observatory and learning the southern hemisphere sky in great detail. This meant that when Oscar looked up on the night of February the 24th, he immediately noticed something unusual. The large Magellanic Cloud, the little satellite galaxy visible in the Chilean sky as it orbits our own Milky Way, had an extra star in it. Oscar knew this was unusual, but it would be several hours before he and his colleagues fully understood what he had seen. The strange new star in a neighbouring galaxy would spark a worldwide fever among astronomers and usher in an era of astronomy not seen since the 17th century. It would also give Oscar a unique place among astronomical heroes. He had become one of only a handful of people in human history to discover a supernova with the naked eye. Imagine a star that's at least 8 times as massive as our Sun. Stars like this lead very different lives, following the live fast, die young philosophy. They only live about 10 million years as opposed to the 10 billion, that's with a B, that our Sun will live. During their lives, these stars maintain a careful balance between the inward pressure of their own gravity and the outward push of energy produced by the nuclear fusion going on in their cores. When a star first forms, its core will fuse hydrogen into helium. Once the core has exhausted its supply of hydrogen, it changes gears and begins fusing helium into carbon instead. This continues through heavier and heavier elements, carbon into oxygen, oxygen into silicon, and then silicon into iron. At this point, the star is now in trouble. Fusing all of these elements has produced energy, but fusing iron takes energy. So the delicate balancing act that has supported the star against its own gravity becomes disrupted. Gravity wins, and in less than a second that iron core implodes. The outer layers of the star go tumbling after it and then bounce off the imploded core, producing a rebound shock that blasts the star's material out into space. The bounce and shock is what we see as a supernova explosion, and what remains from the supernova is either the compact core of the star, a tiny dense husk known as a neutron star, or the infamous endpoint of stellar death known as a black hole. We'll get into neutron stars and black holes in a future program, but it's important to remember that these objects are formed in supernovae, even though they're made by a collapsing star. It's surprising to think that a spectacular explosion like a supernova begins with a collapse, but it highlights the extreme physics going on during the death of these enormous stars. A supernova releases a tremendous amount of light and energy, making these the most luminous events in the universe. Seen from nearby, say only a few thousand light years away in our own Milky Way, a supernova is an incredible sight to behold. A drawing on the ceiling of an ancestral Puebloan dwelling in Chaco Canyon, New Mexico, is thought to depict a supernova that happened nearly 1,000 years ago, in July of that year, 1054. The astronomer who recorded this would have been treated to a shocking sight, a brilliant new star appearing near the horizon around dawn, so bright that it was comparable to the light of the nearby crescent moon, and easily visible in the daytime sky. Records of the supernova also exist from Japanese, Arabic and Chinese astronomers, who refer to it as a guest star. It appeared suddenly in the sky, stayed bright and easily visible in the daytime for several weeks, and then faded away in the night sky over a couple of years. This sudden appearance and slow fade are typical supernova light curves. Remember, a light curve illustrates how the brightness of an object changes with time. We saw these before when we talked about variable stars like Cepheids, which brighten and dim at clear regular intervals. Supernova follow a different pattern. They quickly become incredibly bright and then slowly fade away over the course of about a year or two. The speed of a supernova's brightening and the dimming can tell us a lot about the physics powering the supernova and even what happened to the star during its life. For example, some supernovae fade away in a neat linear fashion, while others go through a temporary plateau, staying fairly bright for a while before continuing to fade away. This comes from the interaction of the supernova shock wave with the outermost layers of the star, temporarily heating those layers until the light they produce dominates the light of the supernova explosion. Light curve shapes are a key tool that astronomers use today in classifying supernovae. However, back in 1054 the telescope hadn't been invented yet, so astronomers were left to rely on their own eyes and whatever notes they made. To the observers in 1054 this astonishing new star would simply have faded away, seeming to disappear into nothingness. It wasn't until the mid-1700s that astronomers would identify what looked like a faint nebulous remnant of gas at the same location in the sky. This object was eventually dubbed the Crab Nebula, since sketches depicting the bright filaments of gas resembled leggy sea creatures. By the early 1900s, astronomers had begun to spot subtle changes in the nebula's shape and to connect it with tales of the spectacular guest star in 1054. The guest star proved to be the luminous and final moments of an enormous dying star 6,500 light-years away. Today, the Crab Nebula is one of the most spectacular known examples of a supernova remnant. The ejected debris from the dying star is expanding slowly from the centre of the explosion, emitting light at wavelengths that span the entire electromagnetic spectrum, from radio to X-rays and gamma rays. The supernova of 1054 wasn't an entirely new phenomenon to the astronomers of that age, perhaps because some of the more senior scientists had seen something like it before. In the year 1006 another dazzling guest star lit up the sky, again visible during the day and so bright it was compared to the moon. Supernovae are relatively rare events. Even with the hundreds of billions of stars in our Milky Way, we only get to see something like 1 or 2 supernovae every century. An astronomer spotting 2 in their lifetime would be an especially exciting event. This excitement repeated itself beginning in the late 1500s. In November of 1572, a supernova appeared near the constellation Cassiopeia, and famously caught the notice of Tycho Brahe. Brahe is something of a larger-than-life figure to science historians, and it's not hard to see why. By 1572, Brahe had enjoyed the upbringing of a Danish nobleman, explored early interests ranging from alchemy to botany, bucked the tradition by marrying a woman of common birth, built an observatory and an alchemy lab at a nearby abbey, and famously lost part of his nose in a sword fight. Still, the supernova stood out as a landmark event in his life, captivating his imagination and cementing his desire to devote his scientific career to the study of astronomy. As with the supernova in 1054, the remnant of the supernova in 1572 has since been spotted, around 9,000 light-years away, and photographed by modern telescopes, capable of detecting the X-rays emitted by the expanding shock wave of the supernova. Today it is commonly referred to as Tycho's supernova. Another supernova happened just 32 short years later, in 1604. Tycho Brahe unfortunately missed this one, having died just 3 years earlier, but the supernova was faithfully observed by his colleague Johannes Kepler. Like Brahe, Kepler identified what looked like a suddenly appearing bright new star, this time in the constellation Ophiuchus, that outshone any other star in the sky and was visible in the daytime for weeks. Like the 1572 event, this 1604 discovery eventually became to be known as Kepler's supernova, with modern-day telescopes finding and studying the supernova remnants. Using a telescope, you can see the beautiful soap bubble remnants of all three of these supernovae, from 1006 to 1572 and 1604. Today, astronomers believe that these three supernovae were caused by a very different kind of explosion than the one that produced the Crab Nebula. They originated from a Type 1a supernova. To understand the admittedly uninspiring name, we need to go back to how we study and classify supernova. We have already talked about supernova light curves, studying how their brightness changes with time. But even more valuable is the spectrum of a supernova, giving us the explosion's chemical footprint. During modern studies of supernova, astronomers began by classifying these events based on whether or not they showed signs of glowing hydrogen in their spectra. Supernova with no hydrogen were referred to as Type 1 supernova, while supernova that had hydrogen were referred to as Type 2. It seemed like a good idea at the time, but astronomers soon learned that dying massive stars could produce all sorts of different supernova spectra. Some stars had lots of hydrogen in their outer layers, making them Type 2s, while others lacked hydrogen and got classified as Type 1s, despite the explosions being incredibly similar. Supernova produced by the collapsing cores of dying stars offer a rich cocktail of different spectra. So today the supernova classification scheme is a miasma of numerals and letters and subletters, all combined to try and explain what we're seeing when a star dies. However, a Type 1a supernova is unique even among the vast array of supernova classes. Instead of coming from a core collapse death of a massive star, a Type 1a supernova comes from the explosion of a tiny star known as a white dwarf. White dwarfs form from stars like our Sun. Our Sun isn't massive enough to die in a supernova explosion, because it never gets hot enough in its core to fuse carbon, oxygen, and the heavier and heavier elements that eventually leave massive stars with those fatal iron cores. Instead, a star like our Sun will slowly expand and cool off, before gradually puffing off its outer layers and leaving behind a small hot lump of densely packed carbon and oxygen, about the size of a small planet. If one of these white dwarfs has a binary companion, maybe another white dwarf, or maybe a star like our Sun after it's cooled off and swollen in size to become a red giant, it could eventually begin to draw mass from that companion onto its own surface thanks to gravity. This process can sometimes ignite carbon fusion on the surface of the white dwarf. This is akin to lighting the fuse on a bomb, beginning a runaway nuclear fusion reaction that eventually blows the star up in a thermonuclear explosion, ejecting energy and matter in an enormous shock wave. Like a dying massive star, the end result is that brilliantly bright shock wave. The difference is that an exploding white dwarf doesn't leave a neutron star or a black hole in its wake. Instead, it leaves nothing behind. There's a lot that astronomers still don't know about Type 1a supernovae. We're pretty certain that they come from white dwarfs, but we're not certain what types of binary companions these white dwarfs need to start borrowing mass from in order to die as explosive supernovae. We're also not quite sure how the fuse is lit on these tiny stellar bombs, or how this fuse ignites a runaway nuclear reaction that can ultimately detonate an entire star. However, astronomers today do think that Type 1a supernova have very predictable light curves, reaching a peak luminosity closely tied to how fast they brighten and then dim. This is why, as we learned in Program 10, Type 1a supernovae are thought to be standard candles. Since these are such bright events, Type 1a supernova can be detected in distant galaxies and used to measure those galaxies' distance with incredible accuracy, serving as a valuable tool for measuring the expansion of the universe. Let's think carefully about the brightness of a supernova for a moment. These stellar deaths are so bright that they can outshine the light from anything else in their home galaxy combined. The astronomers of the 11th and 16th centuries were very clear in their dramatic descriptions of these strange, suddenly appearing new stars. They shone as bright as a crescent moon, lit up the sky, and could even be spotted in the daytime sky. A supernova sounds incredibly dramatic and pretty impossible to miss. So where are they all? And remember, Oscar, our Chilean telescope operator, spotting a tiny new star in the southern sky. How could such a spectacular stellar explosion be so hard to find? The trick comes when we consider the distances to these supernovae. The famous supernova of the centuries past all happened within our own Milky Way, 5,000 or 10,000 or even 20,000 light years away. In astronomical terms, these supernovae were right in our own backyard. The supernova that Oscar saw and the supernova astronomers observe today to study dying stars and the expanding universe are much further away. Oscar's small new star was in a corner of the large Magellanic Cloud, a satellite galaxy of the Milky Way. Unlike the supernova of yesteryear, this one happened over 160,000 light years away, 10 to 20 times further away than the fireworks shows admired by Brahe and Kepler and Oscar's other fellow naked-eye astronomers. The distance meant that the supernova could have been easy to miss for someone who wasn't as familiar with the night sky as Oscar. Oscar checked on what he was seeing again and again as he sipped his coffee that night. It wasn't a plane or a satellite or some trick of the night sky. He knew the Magellanic Cloud practically by heart, and knew this star was a new addition. By 1987, supernovae were a known phenomenon in astronomy, and Oscar knew that astronomers had been searching other galaxies for signs of them. Most searches focused on enormous galaxies with heaps of stars that might be ready to die, rather than small galaxies like the large Magellanic Cloud. Still, it was an intriguing possibility. Later that evening, another astronomer on the mountain named Ian Shelton noticed the same strange new star when he was reviewing glass photographic plates from the night. When Shelton mentioned his discovery, Oscar recorded his early naked eye observation. Together they compiled and sent out an announcement to their fellow astronomers, setting off a storm of activity and excitement as this bright new supernova, dubbed 1987A, named after the year it was spotted, and given the designation of A to mark it as the first supernova observed that year. In the years since, supernova 1987A has become one of the most famous and well-studied supernova of all time. We know that the supernova came from a dying massive star, but its remnant is strange compared to the other supernova remnants we've seen. 3 sparkling bright expanding rings and a bright centre that we've been able to watch evolve in real time. We still don't understand exactly why this remnant looks the way it does. We also don't know whether it's unique to this supernova or just a unique view for us. The first time we've been able to point world-class telescopes at a supernova almost immediately after its discovery. Still, supernova 1987A may seem like a bit of a disappointment. Oscar's observations marked him as one of only a handful of people to spot a supernova with the naked eye. But it also sounds like astronomers of yesteryear had a much easier time of it, with Milky Way events lighting up the sky. It's fair to ask, where are all the Milky Way supernovae? Remember, astronomers estimate that there should be 1 or 2 supernova in our neighbourhood every century. Some supernova have likely happened in our galaxy during the last few hundred years, but they may have been blocked from our view by the galaxy's dense star and dust-filled disk. A simple quirk of statistics puts us where we are today, with no local observable supernova in our own Milky Way for over 400 years. It's especially frustrating when you consider that the last galactic supernova, Kepler's supernova in 1604, happened just 4 years before Hans Lippershey filed the first patent to mark the invention of the telescope. That said, it is fun to imagine what it would look like if we were to step outdoors tonight, look up and spot the next Milky Way supernova. The sight of a sudden new light in the sky, appearing as from nowhere and getting brighter and brighter, might look a bit alarming at first. Once it got identified as a supernova, it would become a global source of excitement, discovered by everyone from national news anchors to social media hashtags. And maybe you, or someone like you, would join Oscar as one of the rare few humans in history to discover the explosive death of a star with the naked eye. Today, astronomers have developed telescopes and software that can do computationally what Oscar did with his eyes and mind, detecting supernova up to billions of light years away. We'll talk more about these computational tricks and how astronomers study the changing night sky in future programs. But first we need to take a close look at how we study supernova and other phenomena like them. These are extremely energetic events, outshining entire galaxies and blasting many suns' worth of mass into the vacuum of space. Our eyes see the visible light produced by supernova, but fully understanding them requires observations across the entire electromagnetic spectrum. We learned earlier about radio astronomy and how long wavelength low energy light can be used to study everything from supermassive black holes to the earliest moments after the Big Bang. Next we'll explore the other end of the spectrum, studying the incredible technology and tricks that astronomers use to study the highest energy photons, ultraviolet light, X-rays and gamma rays coming from the night sky.